Interference of waves. By the end of this lesson, you should be able to state the principle of superposition, explain the interference of waves, draw interference patterns, interpret interference patterns. What happens to the surface of the water when a stone is thrown into it? Waves moving radially outwards are produced. What do you think of water at the same time? Observe the pattern of the waves produced. What happens when two pulses travel simultaneously in opposite directions along the same slinky? Click Start to start the pulses from each end of the slinky. When two pulses meet, they overlap, then continue to move in their original directions. When the pulses overlap, the displacement of the spring, or the resultant amplitude, is the vector sum of the individual amplitudes of each pulse. The combination of two or more waves to form a resultant wave is referred to as superposition. The principle of superposition states that when two or more waves combine at a point, the resultant amplitude is the sum of the amplitudes of the individual waves. When two or more waves meet, they superpose or combine at a particular point. The waves are said to interfere. This phenomenon is called interference. Now, what may happen when two pulses traveling simultaneously in opposite directions meet? Click Start to start the pulses from each end of the slinky. When the two pulses meet, they superpose. The resulting pulse has a bigger amplitude which is equal to the vector sum of the amplitudes of the individual pulses. This is called constructive interference. What do you think may happen if the amplitudes of the pulses are negative? Click Start to start the pulses from each end of the slinky. The resulting pulse has bigger negative amplitude, which is also equal to the vector sum of the amplitudes of the individual pulses. This is also a constructive interference. What may happen if the pulses that combine are out of phase? Click Start to start the pulses from each end of the slinky. If the pulses that combine are of the same amplitude but are out of phase, the resultant amplitude is zero. When a positive amplitude or displacement adds to the negative amplitude or displacement, a zero amplitude or displacement results. That is, the pulses cancel one another. This is called destructive interference. A ripple tank with two dippers has been prepared. Click the button to start the propagation of waves. What can you say about the waves produced? The dippers are connected to the same motor. The two sets of continuous circular waves produced have the same frequency and are in phase. Sources that produce waves of the same frequency and have a constant phase difference are called coherent sources. The two sets of waves interfere with each other. What can you say about the interference pattern produced? Bright and dark regions can be seen. The bright and dark regions are points of interference. At these points, the water moves up and down with a large amplitude. There are also regions where destructive occurs. At these points, the water is actually still. The schematic diagram shows an interference pattern of water waves. The thick lines represent the wave crests, and the thin lines represent the wave troughs. Points A, B, C, and D represent points of constructive interference. These points are called antinodes. Points W, X, Y, and Z represent points of destructive interference. These points are called nodes. The imaginary lines that connect the antinodes are called antinodal lines, whereas the nodes are connected by the nodal lines. A monochromatic light source and a double slit are arranged to produce two coherent light sources, 1 and 2. What can you see on the screen when the two light rays interfere? An interference pattern of bright and dark fringes is seen on the screen. How is this pattern formed? A light wave is a transverse wave. When a crest from one source meets a crest from another source, or a trough from one source meets a trough from another source, constructive interference occurs. When this happens, bright fringes are formed. When a crest from one source meets a trough from another source, destructive interference occurs. When this happens, dark fringes are formed. A sound generator and two loudspeakers are arranged to produce two coherent sound sources, 1 and 2. What can you observe when the two sound waves interfere? Alternate loud and soft sounds can be heard as one moves from point X to point Y. How is this pattern formed? Sound waves are longitudinal waves. The compression regions of a sound wave are denoted by solid lines, while the rarefaction regions are denoted by dashed lines. When a compression region from one source meets a compression region from another source, or a rarefaction region from one source meets a rarefaction region from another source, constructive interference occurs. When this happens, loud sounds are heard. When a compression region from one source meets a rarefaction region from another source, destructive interference occurs. When this happens, soft sounds are heard. Imaginary lines that join the points of constructive and destructive interferences denote regions where loud and soft sounds can be heard. As one moves from point X to Y, he or she is able to hear the loud and soft sounds alternately. Observe the amplitude of two waves experiencing constructive and destructive interference, using the principle of superposition. The principle of superposition states that when two waves superpose and meet at a certain point, the resultant amplitude at that point is the vector sum of the amplitudes of the individual waves. Consider two pulses of the same amplitude traveling towards one another along the same medium. Each crest has an amplitude of 1 unit. What is the amplitude of the resultant crest when the two pulses meet? When the two crests meet, the resulting crest has an amplitude of 2 units. What type of interference does this show? What happens if the crest of one wave meets with a trough of another wave? The resultant amplitude is 0. What type of interference does this show?